Hi everyone. Today we're going to jump into sections 5.3 and 5.4, starting with 5.3, the binomial distribution. So let's start off with the definition. The definition that we're going to have is what's called a trial. And a trial is the repetition of an experiment. So when we do something over and over again, each time we individually do that, we would call it a trial. We're going to use that definition here in just a second. But so here's the idea. In this section, the binomial distribution, bi, of course, meaning two. So what we're concerned with is some sort of experiment that each time we do one of these trials, there's only two possible outcomes. So let's say binomial, one of the keys is going to be two possible outcomes. And so, for example, say we flip a coin. Obviously, there's two outcomes, heads or tails, but let's say that we flip a coin and the question is, did we get heads? So either yes, we did or no, we didn't. Another example of that may be if we're looking and we say, for instance, I'm a salesperson, and when a potential customer comes in, did I make the sale? So we may have a salesperson, and then the question there is, did we make the sale? Again, there's only two outcomes. Either yes, we did or no, we didn't. And then lastly, let's say that we're looking at a person and we want to know if their primary hand that they use is their left hand. So we look at someone and the question is, are they left-handed? And so again, that's yes or no. Maybe they use both hands or ambidextrous. And then we can decide, hey, if somebody's ambidextrous, are we going to count them in there, or is it just predominantly, they're dominantly left-handed? So however we want to do that, but either way, we look to see if a person's left-handed. And again, either yes, they are, or no, they're not. There's only two outcomes. These would all fit perfectly into a binomial distribution. Now, let me show you something that they talk about here. Let me paste this in real quickly. And it's called a Bernoulli trial. And a Bernoulli trial is what we're talking about. These are the type of trials that get us binomial distributions. So if I read through this, it says a Bernoulli trial. It's a repeated trials of an experiment are called Bernoulli trials if the following three conditions are satisfied. The experiment or each trial has two possible outcomes, denoted generically S for success, that means they have the quality, and F for failure, no, they don't have the quality. So the trials are independent, meaning that the outcome of one trial in no way affects the outcome of the other trials. Same definition of independence we saw earlier. And then three, the probability of success, called the success probability, and denoted P, remains the same from trial to trial. Okay, so that's the idea of what we're going on here, is we're looking at these, we're saying, okay, is it a success, is it a failure? And realize there's no determination. Success doesn't mean good, failure doesn't mean bad, it just means success means they have what we're looking for. So if we're looking for somebody, for instance, that is bald-headed, if we find somebody bald-headed, we'd say, success, I found somebody bald-headed. Yes, this person's bald-headed. And we would say, oh, it's a failure because this person wasn't bald-headed. Well, there's no judgment. Is bald-headed good or bad? It's just, if it's looking for, it's a success if they have that characteristic. It's a failure if they do not have that characteristic. So that's all we're talking about there. So in addition to these three specifications, we know if it's a Bernoulli trial, we can do binomial distributions. We can find probabilities that way. I'll show you, we'll do a problem where we find probabilities. But in addition to probabilities, what we're going to do is we're going to find the mean and the standard deviation. So the mean, mu, is just n times p. Nice, easy formula for that. And I'll show you where that might make sense. And then the standard deviation sigma is actually just the square root of n times p, but then times 1 minus p. And sometimes what they're going to say is sigma is the square root of n times p times q. Notice if p is the probability of success, so say p is 0.3, 1 minus p would be 0.7, that's the probability of failure. So if there's a 30% chance of success, there's a 70% chance of failure. Well, that's what q represents there. So in this case, p would be equal to probability of success, and q would equal the probability of failure, where q is equal to that same 1 minus p we see above. So sometimes it's easy to just figure out what p is in your head, and then that's typically what they would do. But sometimes we would just put it into our calculator with the parentheses 1 minus p. It's a little harder to put it in your calculator that way because you have to have that parentheses or else you're going to get the wrong answer. So you may see this formula either way. I noticed I spelled standard wrong. That's not very good. Let's try that again. Standard deviation. That's a little bit better. Oh, okay, so there's my mean. That's my formula for the standard deviation. Just a real quick example of finding the mean. Suppose p equals 0.3. That means there's a 30% chance that we're going to find the characteristic we're looking for. If we do n, that's my sample size, n equals 10 trials, then the mean is n times p. So it's going to be 10 times 0.3. We would expect if there's a 30% chance of any one person having the characteristic, we're going to get 3 as our average number. Out of every 10, we expect to get about 3 people having the characteristic. Okay, and that's just our, of course, our long-term average. We don't expect every time we talk to 10 people, we'll have exactly 3, but the more people we talk to, or this average is going to. Okay, so that's the mean, that's the standard deviation. We'll use those in calculation, but I'm just going to jump into MyLab statistics, and we're going to do a problem to show you how all this works. So let's jump there real quickly. So here's MyLab. Let's look at problem 5, and let's go through this. Okay, so there's a few parts. Notice that they're going to ask us for the mean and the standard deviation, so we'll be able to do that again. It says the probability is 0.3. How about that? That was coincidental. That a traffic fatality involves an intoxicated or alcohol-impaired driver or non-occupant. In 7 traffic fatalities, find the probability that the number y, which involved an intoxicated or alcohol-impaired driver or non-occupant, is. So A says exactly 3, at least 3, or at most 3. So at A, there's 3 different things that we're doing. We're going to start this way, exactly 3. What we're looking for here, and let me write on this, we should be able to carry this over with us. We're looking for the probability that either x equals 3, or you could just say p of 3. However you want to do it. The next one's going to be at least 3. So that's going to be at least 3, means x is greater than or equal to 3. And then the last one where it says at most 3, that means it can't be any more than 3. So it's probability x is less than or equal to 3. So those are the 3 things we're looking for part A. So let's go to StatCrunch and we'll see how this works. All right, so let me jump over to StatCrunch real quickly. We'll open that up, and there it is. So we'll go into where we're doing the homework. I don't know why I left to do that. We're already there. That was silly of me. Let's just click on question help and open up StatCrunch. Okay, there's where I wrote it though, so that we'd still be able to see what the questions were when we do it. Okay, we opened up StatCrunch, and what I'm going to do, and if I remember my numbers right, we had 7 trials and we had a 0.3 chance of getting those. So we go over here and we go stat calculators. And since this is binomial, we come over here and say it's binomial, and it opens up a calculator for us. Now, that's a little unfortunate where that is, but we'll just move this over so you see it. Notice they give me a nice picture for it, but we're going to answer these questions. Well, the probability P is exactly 3. Well, we come over here, N, remember, was 7, so we'll put that in. We have 7 trials. P was 0.3. And then we're going to come down here. We're going to change that to an equals 3. And that's all you do. There's your answer. I don't remember how many decimals they asked us to go to, so we'll go to 4 decimals. That's as much as they would. It's going to be 0.2268. The next numbers are 9. 5 or higher, so we round up, so 0.2269. 0.2269. And now to do the P is greater than or equal to 3, we just change that equal sign to a greater than or equal. Oh, it already computed for us. I didn't have to click on anything. 0.3529. And then lastly, less than or equal to 3. Just change it there. Compute that one. And we get 0.8739. Again, we have to round up, so it's going to be 0.8740. All right, so let's go back. Let's enter these answers, make sure we got them all right, and go to the next question. So now we can flip out of here correctly. So we'll go back to the problem set, and it says the probability of exactly 3. Well, that's what we had here, exactly 3. And what did they say? 4 decimal places is needed, so we're good, 0.2269. Got that one right. Let's go to the next one. At least 3, 0.3529. Make sure you round correctly or you're going to get the wrong answer. And then lastly, 0.8740. All right. So pretty straightforward to get these probabilities. Now they say, well, what's the probability between 2 and 4 traffic fatalities? Inclusive, that means we include the 2 and the 4. So what I'm doing here is the probability X is between 2 and 4. It's greater than or equal to 2, but it's less than or equal to 4. It's 2 or 3 or 4. Well, let's go calculate that. Again, 4 decimal places, so we're good there. So let me open up StatCrunch again. And now we come up here and click where it says between, and that'll change it so that we can say, oh, between 2 and 4. And I compute 0.6417, round up to 6418. 0.6418. All right, let's go make sure we have the right answer, and then we'll get the next question. Click in the box, 0.6418. All right. So we're good there. The mean, well, that's just our formula. So remember the formula for the mean, mu was n times p. Well, n, 7, we had 7 trials, p, 0.3, and when we multiply that, we just get we get 2.1. So out of every 7, we'd expect on average 2.1. Could we ever get exactly 2.1 on 7 trials? No. We have to have a whole number, but that would be our average. And so remember, these are average values. So on every 7, we'd average 2.1. All right, so the mean is, we'll go ahead and enter that in, 2.1. We got the 2.1 correct. And then continue, I don't know why they throw that in the middle of a problem, choose the correct interpretation. In every 7 traffic fatalities, exactly this many will involve an intoxicated or alcohol-impaired driver. No, we can't have exactly 2.1. That's not what it means. That's just an average. On average, that's a better start. Of 7 traffic fatalities, this many will involve an intoxicated or alcohol impaired driver or non-occupant. That looks good to me. Let's see what C said. On average of this many traffic fatalities, 1 will involve an intoxicated or alcohol impaired driver or non-occupant. I don't know where the 1 came from. Clearly not the right answer. Final check. They don't give us a lot of chances on that one. And then D just says find the standard deviation. So we'll go back to the formula. Remember the formula, N times P times Q, or 1 minus P. So we get 7 times 0.3. And this is going to be 0.7, or you could enter that in as 1 minus 0.3 in parentheses. Either way, same thing, but it's that square root. Now, I'm not going to put, when I put this in my calculator, I don't actually put in all of those parentheses. I'm just going to say times. It's just easier to write it that way. Okay. So my calculator, I'm going square root 7 times 0.3 times 0.7. And I get 1.21. They say how many decimal places? 2 decimal places. It's 1.212, so I don't round up. And so I will round it off to, we'll say approximately, since I'm rounding it off, 1.21. Oh. Let's get there. 1.21, got the right answer. All right, so that's the idea. That's how we find some probabilities. That's how we find the mean, interpret the mean, find the standard deviation. I like that problem real well because it gave us the whole range of essentially what that section is. Okay, so you need to understand when you use the binomial distribution, what types of problems. The big key is there's only 2 possible outcomes, success or failure. The other big key is the probability of success doesn't change from trial to trial. And then lastly, they have to be independent. Well, the outcome of one can't influence the outcome of another one. Okay, so let's use that. Let's go into the next section. So let's go back to the lecture material. And I'll from here jump into 5.4, which is the other section we're doing today. And as you can see, I already have some stuff written there. So this is called the Poisson distribution. So the Poisson distribution is often used to model the frequency with which a specified event occurs during a particular period of time. This is the most common way that the Poisson distribution is used. So for example, I may say, how many people enter a store in 30 minutes. And what you want to make sure when you're doing something like this, that all of the times during that 30 minutes, it's pretty much equally likely for somebody to come in during any of those times in that block. So if you've got a big spread in time, that's why we're not saying, hey, how many people are going to enter the store during the day? Because there's going to be sometimes you're busier than other times. And so you want the block to be all a busy time, all a slow time, all an intermediate time, whatever it is. But you want that block to be consistent. Okay, so that would be an example of where we would use a Poisson distribution. Another one may be how many calls let's not say in, let's say to the help desk. Oops, that didn't work too well. How many calls to the help desk in 60 minutes? And again, that time block can be anything. It can be 5 minutes, 10 minutes, 30 minutes, 60 minutes. Again, just so long as it's a block of time where it's a fairly consistent rate that we're taking the calls or people passing by or entering the store, whatever the case is. So those are ideas of what we're looking at. Okay, so we're going to build from that. Again, we're going to find probabilities. I'll show you a problem with that. But what we also want to look at is the mean. To get the mean here, mu they give it a symbol called lambda. And that is a Greek letter, lambda, but they're going to use that symbol, and it actually represents the mean of this, but it's used specifically for a Poisson distribution. Okay, and then the other one, the standard deviation, is going to be sigma is equal to the square root of lambda. All right, so that's the idea. That's the mean. That's the standard deviation. All I'm going to do is I'm going to go through and show you how to do a problem in StatCrunch. So that deviation doesn't look very good, but that's what it spells, a standard deviation. Let's jump into StatCrunch and do a problem. All right, so here's our problems. We'll exit out of that. It's problem number 8 that I want to do. All right, the modeling and solution of problems concerning motel reservation networks for motels were studied. Researchers defined a type 1 call to be a call from a motel's computer terminal to the National Reservation Center. For a certain motel, the number X of type 1 calls per hour has a Poisson distribution with parameter lambda equals 1.4. Notice with Poisson, there's only a single parameter. Remember, parameter just means a value from the population, but it's only got one single value that the whole distribution is based on. That's all we need is that lambda value. And there's a big complicated formula to calculate these one at a time. We don't need that formula because we've got StatCrunch. So we're going to use StatCrunch to do it. So determine the probability that the number of type 1 calls made from this motel during a period of 1 hour will be exactly 1. Okay, so remember, we have this value of lambda that's 1.4. And we just want to know that we get 1 call in this 1 hour. All right, so here's what we do. We jump back to StatCrunch. So let's go click, open StatCrunch back up. And what we're going to do is we're going to go back to stat calculators. This time we come all the way down here to Poisson. And now there's my Poisson calculator. It looks very similar, obviously, to the calculator I had for the binomial. And what I put is the mean. We say, well, what's the mean? Well, remember, the mean is the same as lambda. They told us lambda was 1.4. Okay, probability. Well, they said there's exactly 1 in that hour. So we say equals 1. And then we compute it, and there's my probability. We even have a picture of it. It's just that red bar. Oh, the probability 0.3452. All right, let's write that down. 0.3452. And let's go back and enter it in. That's all we do. We didn't have to put the hour anywhere because that 1.4 was the mean number of these calls per hour. So it was the same units that we had before. So we didn't have to do anything with that. All right, so let's enter this in. We say, oh, the number of calls in an hour, the probability that there's exactly 1, 0.3452. And why did we get not correct? Because I didn't read the instructions. Round to 3 decimal places as needed. Okay, 0.345. Make sure you read the instructions, especially on the test, because you don't get a do-over. It'll just say your answer is wrong. Okay. Determine the probability that the number of type 1 calls made from this motel during a period of 1 hour will be at most 2. Well, if we were going to write that down, at most 2, that means the probability of X less than or equal to 2. At most means 2 or fewer. It can't be more than 2. So that's what we have there. Let's just go ahead and put an equals there, and we'll go calculate that one. So let's back to StatCrunch. And there it is. So we've already got the parameter in there. We're okay. We're just going to say less than or equal to 2. And I'm pretty sure that's what I wrote down. Let's look. Oh, yeah, there it is. Less than or equal to 2. I did. 0.833. Now this time I'm only going to go to 3 decimal places because this time I'm actually paying attention. All right, so I've got that. Let's go back into StatCrunch, or rather into the homework, and enter that answer, 0.833. Hey, this time I'm the right number because I have the right number of digits. Determine the probability the number of type 1 calls made to the motel during 1 hour will be at least 4. Now, they say use the complementation rule because when they're calculating this, they can only calculate one at a time. And if there may be 100 calls, you'd have to do at least 4 would mean 4 or more. So you'd have to find the probability of 4, 5, 6, 7, 8, 9, 10, 11, 12, forever until at least you get to less than 0.000. So you're not going to add any values to it. So they would do 1 minus the probability of 0, 1, 2, and 3. Good heavens, that's going to take a long time to do. Luckily, we don't have to. We're doing the probability x is least 4, so greater than or equal to 4. We don't use the complementation rule, so be careful about their hints that they give us. It doesn't help us out. So we go back in and we say, hey, give me a greater than or equal to 4. Oh, 0.054 rounded off. 0.054. So I do round up because that next number is 7. .054. Got that one. On a roll. We're almost done. Find and interpret the mean of the random variable x. Well, remember the parameter lambda is the mean. So the mean is 1.4. The mean is 1.4 calls, and therefore there is, or there are, on average, that's what mean means, 1.4 calls per hour. From where to where? Well, it says right up here, from a motel's computer terminal to the National Reservation Center. So that's what I'm going to put in. So from a motel's computer terminal to the National Reservation Center. Let's get rid of all this so I can actually see what I'm doing. All right, so we look good. Check answer. Fantastic. I like to hear that. And the standard deviation, well, remember the standard deviation of this is just the square root of lambda, which is the square root of 1.4. And we want to go to 3 decimal places. So I'm just going to, in my calculator, go square root of 1.4, and I get 1.183. All right, that looks good enough to me. $1.183. Yep, looks good. All right, so that was it. That's essentially what I want you to learn in this section. So these 2 sections, pretty straightforward, not a lot of lecture going on. Just try these problems. On the homework, there's only 1 problem from each section, rather 2 problems from each section on the homework. So I think that's very doable. Notice in this whole chapter, there's only 8 problems. We just did 2 of them right now. So we did a quarter of the material just in the last 5 minutes or so. All right. So with that, I'm going to stop for the day. That's the material. That's the end of this chapter. Next, we'll jump into chapter 6, and we'll see what's going on in there. So until next time, best of luck to you. Do your homework, and I will talk to you again soon.